Okay, thank you, it works now. Okay, this framework allows the authoring of terrains effortlessly. We depart from the standard elevation representation of digital terrains and in favor of its gradient. And as you can see in a few user strokes, the user can instantly obtain landforms features in an intuitive manner. Altitude constraints can be defined as a set of hard constraints combined with gradient prescription that will influence the solver in the direction of the steepest slope. User control is central in this framework, as you can see and as you will see in the presentation. So let's start with a few examples of user interaction. Here are some examples of user editing sessions. The users effortlessly created a canyon, a cliff, and a mountain range, as you can see. And it also supports seamless copy and paste standard operations. So let's do a bit of related work. Although a vast variety of terrain generation exists, only a few address interactive authoring. Our work allows for real-time interaction with intuitive control and can be compared to the work of NID 2010 and GAIN 2015. The procedural approach by NID and colleagues in 2010 uses diffusion curves to propagate altitudes and slopes around constraints. The main drawback of this technique is that it generates terrains from featured curves and cannot be used for processing and or enhancing terrains produced by other methods. Another texture synthesis approach proposed by Guerin and colleagues in 2015 has very similar use cases. It allows the user to place constraints that direct the texture synthesis algorithm. In comparison, our work provides a unified terrain representation. It is compatible with pre-computed topography and does not depend on exemplars like texture synthesis methods. So let's go for the pipeline and the framework, the formalism of the method. The gradient of the elevation is central to our framework. The gradient combined with constraints implicitly defines the model. The elevation can be obtained by the reconstruction by solving a Poisson equation. Conversely, the gradient can be computed directly from the elevation. This dual representation allows us to utilize both standard algorithms operating in the elevation and gradient domain methods. Gradient-based algorithms are attractive in the scope of terrain modeling because of the gradient being representative of the slope, of course. Thus, we propose both local and global tools for authoring details and generating a gradient map from scratch. Let us review the formalism of our dual elevation gradient framework. Let's start with the easy part, the elevation. We define the terrain as a 2D scalar field H that indicates at each position the altitude. So this is very simple. And the gradient is a 2D vector field G computed from H. Since we operate on a grid, we use, of course, the discrete version of the gradient. Now let's continue with the reconstruction of the elevation H from gradient G. Since solving such another constraint system is not possible, we have twice more equations than variables. We reformulate it as a standard Poisson equation. We compute the divergence of the gradient field and use this as the target Laplacian of H. We combine this differential equation with directlet constraints that we can set anywhere onto the grid, not only on boundaries. And this is very special in our solver because the majority of solvers do not enable the positioning of constraints everywhere onto the map. So these constraints can be punctual, can be curves, and can be also surfaces. We implemented a fast and efficient solver that can be seen as half a V-cycle in a multi-grid algorithm. Note that the compute shader implementation is available on GitHub on the following address. Constraints, as you will see, are essential in the framework. They are of two different types. Gradient constraints are set by prescribing the gradient field. This is what you can see on the left side. And those constraints are not always satisfied by the reconstruction process and direct the generation of the elevation. So this is just a guide to the reconstruction. We call them soft constraints because they are not always respected. On the contrary, directlet conditions enforce the elevation at precise locations onto the grid. They are always respected, and therefore we call them hard constraints. Here you can see an example of the successive iterations of the solver that refine incrementally the solution. You can note that the size of each grid is a power of 2 plus 1, because in a multi-grid formalism, it's far more easier to implement. Okay. Using now combinations of soft and hard constraints, it is convenient and effective to create landforms, archetypes such as crests, cliffs, rivers, faults, or ravines. Hard elevation constraints are crucial, in particular for riverbed landforms, where it is important to guarantee that the terrain has a consistent flow direction without sinks. In other contexts, it is convenient to set soft constraints exclusively and perform an additive effect. For example, in the fault example that you can see on the slide, two faults were superimposed to obtain a complex cliff. Copy and paste operations are usually performed in the gradient domain to obtain a seamless blending. This is kind of the effect that you can see also in the fault example. Because the gradient representation is a vector field, we can modify it using 2D tensors. A 2D tensor will tend to bend the gradient in a given direction, and this direction is guided by the theta angle that you can see in this equation. As you can see, this has the effect of orienting the slopes in a given direction. Note that the tensor can vary depending on the position guided, for example, by a user brushstroke, and the user brushstroke could make an influence on the direction of the tensor. We can also build complex procedural primitives. It is also possible to obtain these complex primitive by using combinations of constraints to build high-level tools and brushes. For instance, on the left, we have built a mountain brush that consists of the creation of a gradient field around a crest line, combined to a tensor-oriented noise to mimic erosion features. So this has the effect of building from scratch something that looks like a mountain. And it's very easy to use in terms of user interaction. And on the right side of this slide, you can see an example of hard constraints that can be combined at different altitudes to obtain this mesa effect. DEMs, digital elevation models, are usually represented by images, so-called height fields, which simplifies their manipulation, of course. We can transpose this to the gradient using two channels of the image to represent the two components of the gradient. This has the advantage to being able to use standard image algorithms, but applied in the gradient domain. So the image that you can see in the center of the slide is just the representation as an image of the gradient. It resembles some normal maps that you usually see. We successfully applied this to super resolution, filtering, texture synthesis, and other machine learning methods that we will see later on. So now let's talk about, we have seen local additions. We will now see global terrain synthesis using gradients and constraints, of course. First of all, we can try to represent the terrain using only hard constraints. So what did we do here? This illustration indicates that our solver can combine hard constraints also with soft constraints that are built procedurally. Here we have extracted the crest and rivet lines of an input terrains, and the lines, these constraints, were used to prescribe hard elevation constraints. In addition to that, we generated a tensor-oriented noise to simulate erosion patterns. This process allowed us to approximate the original terrain using very sparse information encoded in the hard constraints, because all the rest were generated procedurally. So this is kind of a compression algorithm, actually. This example shows the effectiveness of the gradient representation of terrain for super resolution applications. It turns out that the super resolution is more efficient when performed in the gradient domain. In this example, we trained a state-of-the-art super resolution method using gradient images that I presented just before. So this is just a state-of-the-art algorithm. We just changed the data set that we used to train. And the method that we used is called SR-GANs. It's a standard state-of-the-art algorithm. The experiments show that it's difficult to differentiate the super resolution output from the original elevation, as you can see on the right side. This example also illustrates the difference between learning from the elevation and learning from the gradient. The leftmost image shows the input river network that we have used. And when using height, the synthesizer produces visual grid artifacts and smooth spots. And when I say using height, this means that we have used the standard pix-to-pix algorithm to transform the figure that represents the river network into directly altitude maps. Changing to the gradient domain, so this means swapping to generating a gradient image, and also using a data set that represents gradients, removes the artifacts and use sharper and more realistic landforms. Moreover, the gradient prescription combined with elevation constraints allows us to post-process the model and enforce the river network to flow, which was not the case for the elevation. We could have tried to force the model to flow using, for example, erosion algorithm, but this is much slower. Regarding the performances, our solver is real-time, up to a resolution of 1,000 pixels. And above this resolution, we get only interactive times, but it's still usable. The memory footprint in the GPU is limited and only gets higher than 1 gigabyte when using very big maps of 8K by 8K. We tried to compare to the work of NID and colleagues that I talked to in the introduction, in the related work. And in their paper, they present this scene that you can see on the left-hand side. And this was authored in 45 minutes in their software. We tried to author a similar scene. This is not exactly the same, of course, but this looks like similar. And we only spent 5 minutes to obtain the result that you can see on the right side. Our approach shows less artifacts in the reconstruction because of the natural continuity of the solver. And this was not the case for NID 2010 paper, and I'm aware of that because I was also a co-author of this paper. It also has a simpler direct interaction and more high-level tools that allows the inexperienced users to easily manipulate the tool. We performed two different types of validation experiments. First, we asked our artists to test the framework and provide feedback on the effectiveness of the authoring tools. They could also report comments on the user interface, and they found the tools very effective and intuitive, and managed to create examples conforming to their intent. And the examples that you see were not performed by artists. I will talk to you about that later on. Moreover, artists encouraged us to display physical parameters in the interface, such as the altitude in meters, for example, and the angles in degrees, which was not the case before. We also asked non-artist users to author terrains according to a simple text-based description, and within a 10 minutes time limit. The three images that you can see on this slide show several examples. For example, a Y-shaped canyon, a volcano, and a mountain range. The description was as simple as this. Please try to author a Y-shaped canyon. And almost all users pointed out that the tools were easy to use with a quick learning curve. So in conclusion, we introduced a versatile model for terrain authoring that allows for high-level and intuitive interactive editions. And of course, there are several avenues for future work. In particular, terrain stylization and example matching brushes would be valuable tools to incorporate into this framework. And we already tried to do that. We hope that this presentation demonstrated the effectiveness of gradient domain operators. And I'd like to thank all the persons that have been involved in this work that are displayed here on this slide. Thank you.
Thank you very much, Eric. Yeah, we have time for questions. Please don't be too shy. I will try to bring the mic to you if somebody raises their hand. Or there's another person. Maybe you go to the other side, yeah.
Hello, and thanks for the presentation. I was wondering, a very interesting result is that the gradient domain learning is more effective than direct height learning. How did you validate that? Is that only from feedback from artists, which is already a very nice result, or was there more validation involved in that?
Actually, the validations that we performed were already presented here. And I would say that gradient is not the only thing that is important here. The dual representation of using elevations and also gradient to guide were essential in this work, because actually I have started this work almost 3 years ago, and the introduction of hard constraints was only in the last month, and this is where we finally managed to do something that is very usable by artists. And this was acknowledged by artists, as I said. And this is very important to have these constraints, hard constraints, because otherwise it's very difficult to control.
Okay, thanks.
Yes, it works. Yeah,
it works.
Sorry. Would it be very difficult in your tool to extend it to actually mix the both domains, height and gradient?
I'm not sure to understand the question, but these are totally
I think you're
dual.
authoring using the gradients, am I right? Yes?
Yes, but we have always the two representations in memory. which means that when we modify the gradient, we reconstruct and we have the height. But if you want to forget the gradient or forget the height constraints, you can just reconstruct the height and come back to the gradient again. And this will have the effect of erasing all the hard constraints. So we always have this dual representation in memory, but sometimes they are not totally synchronized because, as I said, the gradient is not always satisfied. If we want it to be satisfied, we have to do this, these two operations, reconstruction and gradient computing again.
There's a question here.
Thanks for the nice presentation. I was wondering, so you said it's not exactly example-based, right?
No,
so
not at all.
Yeah, so I mean, from the title, I can say it's more about authoring.
Yeah.
So so in the pipeline, once there is any editing done, does it also have to go back to the full pipeline so that the features are somehow extracted?
I showed several examples where we have different use cases, and sometimes you use these crest lines, sometimes you don't. You do whatever you want, actually. I'm not sure to catch the idea of your question.
Because you mentioned that you use pix-to-pix to kind of get the features, like all these things, to encode that from the gradient field or network.
Yeah.
Into
This
that,
is
right?
one example of generating a gradient map from scratch.
I see.
And this is not included in the authoring pipeline.
I see.
This is totally outside.
Okay.
This was an example of, this is nice to use gradient generation because it generates nicer features, but it's not included in the authoring tool.
Okay. Thanks a lot.
Hi, nice paper. I have a question. So on this video that we see on the screen right now, I have the impression, and I think it's the case, I see erosion-like patterns around the letters, but you are not running erosion, right?
Yes, I am.
Oh, then okay.
Okay, perhaps.
But I just wanted to ask, because I have the impression that if you add noise in a certain way in the gradient space, then you will get this kind of patterns for free, right? Is it the case?
Yes, for free, because you don't have to perform an expensive erosion. But actually, in the tool, we included the erosion, but it's very easy to implement it because we can just perform the erosion in the height domain, compute the gradient again, and inject it in the gradient field. So it's easy to implement it, but of course it's more complex, more expensive to run than just noise oriented by tensors around features. But you see, it's
fast.
Not interactive because the time has been accelerated here, but it's almost interactive.
Okay, thank you.
One last question? No? Thanks for the great presentation. The second presentation is deep reconstruction of 3D smoke densities from artist sketches, and will be presented by Byungsoo King. And it's a collaboration with a number of people from ETH and INRIA.
So, yeah. Hello everyone, I'm Byungsoo. So, thanks for coming to my talk today. So, I'd like to present our paper, the reconstruction of 3D smoke densities from artist sketches. Right, so filmmakers and video creators often use storyboards to transfer ideas from their mind to the screen. And this is a very interesting example. And in pre-production for Raiders of the Lost Ark, Steven Spielberg asked illustrator Ed Verrox to draw storyboards for the climax of the film. And all right, so, and see how closely they guided the final film imagery. We see the great use of sketch and shading in storyboards to represent a mysterious energy stream around, but they're used for the purpose of communication rather than a final visual realization of 3D flow. So the natural question is, can we transfer these concept sketches directly into 3D volumetric flow structures? And traditionally, modeling density volume is performed by detail synthesis on coarse shapes. So once a guide mesh or a sketch is given, then texture or noise is procedurally synthesized to fill out the guide with high-frequency details as a post-processing or even during a rendering time. But these methods are, however, limited to capture intrinsic flow details in the modeling step. Therefore, we present the first method to compute a 3D smoke density field directly from 2D hand-drawn sketches. In our method, we aim to reconstruct smoke density fields from shading-based artist sketches in order to integrate flow structures already in the modeling step. The main purpose is to bridge the gap between early-stage prototyping of smoke keyframes and visual realization. Notice that although 3D smoke reconstruction from 2D sketches is heavily under-constrained, our method gives plausible results. Again, such a sketch-based reconstruction is an ill-posed problem due to the sparsity of sketch data and the ambiguity when inferring another dimension. And previous work indicated the use of convolutional neural network is especially powerful in such tasks. To the best of our knowledge, our work is the first learning-based sketch method for turbulent density volume reconstruction. Another interesting direction parallel to our work is fluid reconstruction and editing. For instance, 3D fluid densities and motion have been reconstructed from image sequences, and sketches have been used to control the motion of liquids or 2D flow field generation. All right, so before talking about the details of our method, I'd like to explain our fluid sketch principle first. Sketches are the primary control tool for the artist during the authoring process, and sketching fluids requires a specific style and a workflow. So here we summarize the style decision. Firstly, our target is a chaotic nature system, so we don't impose any geometric constraint on the structure. Secondly, according to the design principle of effects drawing, we keep it simple without random details while still keeping its generality. Thirdly, our style is made of strokes with varying shading and thickness, similar to many other modeling techniques. Lastly, to express the variations of curvature of smoke objects, we impose a two-color tone shading with the light source. And this is our final guideline about strokes and shading for sketching fluids. And we'll see how artists took advantage of our sketch style for drawing later. A major challenge of sketch-based modeling lies in the depth ambiguity and occlusions that cannot be captured from a single viewpoint. Thus, we progressively refine sketches at different angles, inspired by previous work, Deussen et al.'s work, and hence iteratively update and relocate smoke structures. And finally, our method delivers two key properties while authoring. First, the output density volume seen from target view should correspond to the input sketch. Second, the occluded part of density volume must be preserved to ensure multi-view stability. Let's go over our pipeline. So we propose a simple method called initial volume modeling to create an initial guess from two sketches in canonical views. The basic idea is to extract contours and a foreground to compute a visual hull of given object. And at test time, the updater network takes a pair of sketch and an input, the density volume as input, and computes a residual to correct the volume. By rotating it to arbitrary viewpoints, the result can be iteratively refined. And at the end, the subsequent post-processing GAN synthesizes additional fine structures. At training time, we use a semi-supervised training strategy to enforce two key properties already detailed. The single view accuracy and the multi-view stability are well targeted by our carefully designed loss functions. And the key ingredient is our novel synthetic sketcher for smoke volumes, producing sketches that are compliant with our sketch guidelines. Right here we show the output of individual passes at test time. First we compute the initial volume and then alternatively optimize the front view, left view, and front view, left view, again on density reconstructions with our updater. The intermediate density reconstructions and corresponding sketch representations illustrate the convergence after multiple passes. We found that these two subsequent refinement steps already show decent quality of convergence. Now let's move on to our loss functions. In each pass, we calculate view-dependent losses. First, density loss compares the reconstructed volume with the ground truth, and the sketch loss compares their corresponding sketch representations. And depth variation loss is additionally designed to suppress the depth ambiguity from sketch loss. Lastly, our full objective is defined to preserve reconstructions of all input viewpoints. So we evaluate the impact of different loss functions and illustrate the results. Baseline is only with the density loss. We see there is no detail preserved. And if we use only sketch loss, we see very detailed result, but at the cost of depth ambiguity. And if we use both density and sketch losses, the result looks good at sketches, but there are still some artifacts in the depth axis. And finally, when depth variation loss is added, our result looks quite close to the input sketches while reconstructing plausible volumes. Another study on the multi-view stabilities. So we trained the network on a different number of passes and evaluated the quality of convergence while refining on the same viewpoint. Training with a single pass shows lots of dissipation over updates. With two passes, it shows much better convergence, but still losing its stability over iterations. And from 3 passes, we see our method achieved multi-view stability, and we use these 3 passes in practice. So coming back to the pipeline, I'd like to go over our sketch generator, which is at the core of our method. Our differentiable sketcher allows us to automatically annotate smoke data without necessity of storing and to directly incorporate it into the loss functions during training. And these are great advantages to secure the stability and the robustness of the model eventually. Previous techniques typically extract contours from meshes and cannot be directly applied to amorphous shapes such as smoke densities. Although isosurfaces can be extracted from the density grid and converted into mesh as seen in the left image. But the choice of the ISO value is not obvious, and typically low density values details are lost in the process. Meanwhile, for cartoon rendering of smoke, particles have been used and traced through the underlying fluid grid and then rendered as textured billboards. Both methods, however, do not work directly on volumetric data. So our differentiable sketcher generates corresponding sketches on the fly for the end-to-end training. Our method is inspired by the absorption and smoke rendering and estimates a normal map. We average normals for a range of density isosurfaces at the visible boundary of smoke. Then contours are extracted, followed by color tone shading to provide more information about volumes. We combine those to compute a sketch, finally. Oops. And thanks to our lightweight sketcher, we can create infinite number of variations in sketch style to increase the robustness of our model during training. We augmented the sketches for brightness, contrast, contour, strength, tone shading, color, blurring, slurring, and the different light directions as well. And at the end of our refinement, we use a second network to synthesize a flow of details onto the reconstructed density. And this will help artists to alleviate the necessity of drawing small-scale structures, which is to enforce simplicity, one of our fluid sketch principles. We use the architecture of multipath GAN without using temporal discriminator, as we focus on individual keyframes without taking care of any temporal consistency. And this model requires an underlying velocity field in addition to the density field, so we create a synthetic flow field using kernels at test time. Note that it also gives us controllability by parameters. The generality of our dataset plays an important role for robust and high-quality reconstruction of diverse scenes sketched by artists. So those sketches can include both physically inspired and non-physical shapes and motions of smoke. Therefore, we built a new dataset consisting of smoke densities, which captures a large variety of volumetric shapes. We run the simulation in Houdini with the randomly changing temperature diffusion factor, and so on. And this comes along with the sketch augmentation techniques for increasing robustness of our method. Right, here we show the reconstruction result of training data. Top row shows front view, bottom row shows left view. And from left to right, we see input sketches and our sketches from reconstructed volumes and ground truth. And only minimal differences are visible between input sketches and the sketches of our output. And we see the reconstruction result of unseen data during training. Still, we see only subtle differences in sketches. Note that the reconstructed density is smoother than the ground truth. This is because the sketch lacks complete information about the original density and implies the ambiguity of several possible densities corresponding to a given sketch. While an alternative could be to use a sketch style that also encodes fine flow structures, but we prefer to follow our sketching principles and to synthesize high-frequency details in the post-processing. We show that our method generalizes well to various scenes. First, we tested our model on data from physics-based simulations. From front and left sketches are generated using our sketcher. and the reconstructed density closely matches the footprint of input sketch. We measure the quality of inner details by comparing the input sketches with ours, where we see that the shading and inner contours are well captured. Note that the given density cannot be directly compared to the reconstructed density, as our updater focuses on the low and mid-level frequencies to be close to the input sketch. Another interesting test case is non-smoke shapes. Like we selected some frames from animation sequences. Note that these are difficult cases for our model, as they show thin extremities or occlusion, and there was no comparable examples in our training dataset. Nonetheless, differences between sketches are still minimal, demonstrating that our method is not only able to reliably reconstruct unseen shapes, but especially also handle non-physical inputs. Finally, we demonstrate our approach on 3 real-world world applications. We first present the 3D smoke results using sketches from multiple different artists. We instructed the artist to sketch keyframes of smoke or an imaginary smoke-like object. Our method works surprisingly well for such highly non-physical examples. The reconstructed density and sketches closely match the input sketches from the artist. Note that the reconstruction is also robust to variations from the prescribed sketch style and can handle inconsistencies of shape and shading between different viewpoints. So as a second application, we implemented the Houdini plugin for interactive smoke field authoring. Here we show selected sessions, and it took the novice users only a couple of minutes to create, edit, and render the final results. And interestingly, our sketch provides them with an estimate of sketches as a guidance from unseen viewpoints. And we can see many imperfections, such as not corresponding front and side input sketches, or sketch style variations, or gap between strokes. But even in such challenging cases, our method could reliably infer the 3D shapes. And let's have a look at some results from our artist, like novice artists. All right, so as a last application of our method, authored smoke keyframes can be used for target-driven fluid simulations. We used 2 reconstructed frames from sketches, and the resulting animation showed that the simulation matches the target density keyframes, while generating intrinsic flow structures due to the dynamics by underlying physics solver. As one part of evaluations, we compared our results with those of Stever et al., which is surface-based modeling followed by filling with the noise particles. The results indicate that our approach can reconstruct intrinsic flow details more realistically than counterparts. We also demonstrated the user study to evaluate our results with respect to the overall similarity, outer and inner contours, shading, and similarity to the real smoke structures. And overall, our method clearly outperforms the previous work, except for one reality question. Additional study with the users of authoring tools also imply that our tool is useful for early stage prototyping, satisfied with the quality of results, and the sketchy style is intuitive. So in sum, we propose a method, the real-time iterative refinement method for small volumes from sketches. And at the core of our method, there is differentiable sketch generator with the fluid sketch principles. We also provide carefully designed loss functions, data set, and augmentation for a robust model. Lastly, we demonstrated the 3 applications, like artist sketch test, interactive authoring, and animation control. First, there is rooms for improvement, and for now, our method is limited to unscalable and simplified representations, and also we're not supporting the arbitrary drawing style. And yeah, that's all from my side, and thanks for your listening.
Thank you very much for the interesting presentation. I see a number of hands going up. Maybe you were the first. So
Sorry, Joanna. Thank you very much for the presentation. It was quite interesting. So the style of the drawing that you're imposing to the artists is based on your NPR rendering, right?
Yes.
I was wondering if you had feedback from the artists about what would be more natural, maybe, or more. Is it natural for them to draw in this style, and did they provide some feedback that would help make it more natural?
Yeah, I mean, yeah, we got some feedback from the artists and the novice users from both sides, and yeah, they were more or less satisfied. I don't remember the exact number on the study, but yeah, usually they're satisfied with the styles. And even though they try to follow our like guide sketchy style, but they sometimes just found that it just works with some random styles as well. So they found that it was pretty flexible.
All right, so it was easy for them to adapt to. Okay, thanks.
So maybe I can step in. How long did it take the artists to create this sequence of inputs?
Typically, so they usually like start from some like drawing the contours first, and then fill out the inner part with some gray things, and then try to add some inner contours with some shadings. So considering that, they easily get used to that kind of sketch style within, I don't know, several minutes, and then with some practice, and then immediately started to drawing something.
Hey, thanks for the very nice talk and work. I was curious to know your first prediction of volume. I bet it's taking all the views at once, right?
All the views. So for the initial guess, we just use the front and left views. Like it's kind of carving. And
okay, so the user always have to provide a front and left view.
We can still use, if there's only a single view, then we use that one for the front and left views. So still possible to generate initial guess with the single image.
Okay, thank you.
Thank you for the nice presentation. So I wonder, what color palette artists have to write their sketches? Because your method uses like the contour line in black and light color and dark color. These 3 values you use to train your network. So it is it is possible that when test time, artist also uses a limited color palette, like consisting of dark and light and sketchy. But yeah, I wonder, does artist use like arbitrary color palette or like limited set of color palette?
For now, we don't support like a fully arbitrary sketching style, because we just try to push like some standards about the color of background, foreground, and then some shading like color. But yeah, it would be nice to really increase the variability. Mm-hmm. For instance, we're thinking about like a standardizing part to take arbitrary sketch style to like transform into our like standardized sketch style as well. So it can be a future work, I think.
Yeah, thank you. That should be interesting.
Very nice work. So I was wondering, like, can you remind me, like, how do you do rendering of this? Like, once you have the sketch ready, do you perform physically based rendering, or is it also reconstructed from some kind of data set, for example, which is used before to get the appearance?
Those kind of renderings were rendered using Houdini, but we use a differentiable smoke renderer for during the we also try to incorporate this differential smoke render in during the training as well. I think we included in that study in the paper, I think.
I see. And does that make it also relightable? For example, if you want to change the lighting at different places?
Yeah, so we also support the lightings and stuff. Yeah.
Very interesting work. Thanks.
Thank you.
Yeah, thank you for the presentation. I'm going to come back to the color question. If you wanted the final volumes to be colored, what would the main challenges be? Because you said you had to use very few colors for your training.
Yeah, for instance, if it should have, if the color doesn't affect the structural volume, then we can simply try to, pick that color into put into the pipeline and try to render with that color, so that it can be incorporated into the training pipeline. If the color affects the structure, then we have to somehow, come up with the idea how to really each color, how it affects the structures. So haven't thought about it yet.
One last question, maybe? Oh, now I have to. Maybe we can do both.
Thank you for the presentation. So, at the end, you're showing us animations, but we only have sparse steps all in between, but it looks really coherent. So, how did you interpolate all the data?
Except for the last one, we only reconstructed the keyframes only, only the separated frames. For the last one, we use reconstructed frames as a keyframe to do the target-driven fluid simulation. So last one was generated by fluid simulation, basically, which is targeting the given, the density from our tool. And we also tried to do some keyframe interpolations as well in the previous submissions, but didn't include in this submission, actually.
Okay, thank you.
Very last question. Bye.
The input of your algorithm is a set of static images, keyframes. Would it be possible to introduce some dynamic information like streamlines drawn by the artist or something like that?
Yeah, that's actually a very interesting future direction. We only focus on the static frame reconstruction, but we need to use this one for, at the end of the day, we're going to use this for dynamics. So it would be nice to already provide some sort of a dynamics constraint for the keyframe, the target-driven fluid simulations and so on. That would be an interesting idea, actually.
So let's thank you again.
Oh, okay. Hello, everyone. This is Ruizeng from University of Science and Technology of China. I'm glad to present our work, interactive editing of discrete Chebyshev nets. Discrete Chebyshev nets are called meshes with all edges of equal length, which are inextensible along the edge directions. They have been widely used in many fields, such as architecture, packaging, and art. Since such nets are very useful in practice, it's desired to design them in a short time. However, if we want to regenerate a new Chebyshev net by deforming the original triangle mesh, it takes lots of time and may violate the user's design intentions. For example, the singularities which are colored may not be placed at the desired positions. Our goal is to edit discrete Chebyshev nets via a handle-based interface interactively. There are three basic requirements. First, the mesh after editing is still a discrete Chebyshev net. As an approximation, we require the maximum difference in edge length to be small enough. Second, handles reach the positions specified by the users. Third, the editing process is fast enough to achieve an interactive rate. There are two main challenges. First, we need to constrain edge length directly. That's different from isometric constraints because deforming discrete Chebyshev nets has shared degrees of freedom. We show a figure here. The results all preserve edge length by different methods, but they are quite different because of freedom on sharing. Second, constraining edge length is a nonlinear and non-convex problem. So it's challenging to solve this optimization problem at the interactive rate. Let's review previous methods at first. Salkin and Mark constructs local rigidity energy to describe the isometric constraints, but that's different from edge length constraints. Basile et al. Uses local global solvers to solve shape constraints, but it cannot constrain the maximum edge length deviation to be very small, as we show in the bottom figure. As for geometry optimization, Tang et al. Adopts the framework to deal with the minimization of composite objectives, but it doesn't solve the edge length constraints. So there is no previous technique satisfies all requirements. Next, I will introduce our method in detail. Our input includes a discrete Chebyshev net handles and their target positions. We hope that after deformation, each handle reaches its target position, and the edge length remain unchanged. Since the second requirement is strict and too hard to meet, we use a soft constraint energy function and let it approach zero as an approximation. We use the infinite norm to define a constraint energy function, which can describe the maximum edge length deviation. Due to the non-C1 continuity of the infinite norm, it's difficult to directly optimize the L sub maximum to approach zero. So since LP norm with a large P is a good proxy to approximate the infinite norm, we adopt the LP norm to define a new objective function. However, we observe that optimizing this function needs many iterations to obtain a small DL sub maximum in our experiments. Therefore, we construct another new objective function, which is based on the following inequality. As shown in the figure, the new function decreases much faster than the old one near our target. We plot the new function with different p's. When p gets larger, the decreasing rate gets faster. We construct the new objective function, and we found that optimizing the new function is more effective than optimizing E sub p. Our problem can be formulated as a constraint optimization problem. Our method relies on a second-order solver. After getting the inputs, we first compute a Hessian matrix of the energy function, which is further modified to be a positive semi-definite matrix. This is the main step of our method. Since we consider the linear constraints of the handles, and we solve the KKT system to compute the descent direction. Third, we perform a backtracking algorithm to determine the step size. Finally, we update positions of vertices and judge whether terminating the solver or going to the next iteration. Since our objective function is the sum of the energy on each edge, we construct the modified Hessian matrix by computing on each edge. We propose a novel convex moderator for our objective function. First, if a function can be decomposed as the sum of a convex function and a concave function, then we can construct the moderator and manerator of the function at a point x sub 0. And they satisfy the following properties. First, the moderator is convex and the manerator is concave. Second, their values and gradients at x sub 0 are all equal to the original function. Third, they can constrain the value of original function globally. If a function has a composite form, and the composite functions all have convex concave decompositions, then we can construct their moderators and manerators. If the moderator of the outer function can be further decomposed as a sum of an increasing function and a decreasing function, which are all convex, Here, increasing or decreasing is with respect to each variable when all the others are fixed. Then we can construct a function which can be proved to be a moderator of f. In our method, the beginning steps are similar to Stangle et al.'s, but the further decomposition and moderator are different from theirs. For our objective function, we can decompose it to a simple form and construct the convex moderator. Then the modified Hessian is computed as the Hessian matrix of the moderator. Now I will revisit the method of Stangle et al. It constructs its moderator by constructing modified inner functions. Our moderator is different from theirs, and our solver provides another way to construct a moderator. We have the follow proposition for the differences between the two moderators. Although this proposition shows our moderator is greater than that of Stangle et al.'s, we think a tighter moderator cannot guarantee better global performance in theory. That's because tighter is more local and tends to be more effective when near the global optimum. But it may lead to insufficient degrees when far away from the global optimum. We found that Stangle et al.'s moderator considers influence of G, depending on value of partial derivatives of H. For our function, since G sub E is convex, it doesn't use value of G sub E when H is decreasing. We propose our decomposition to take the Hessian of G into consideration in this case. Our moderator uses the further decomposition regardless of the value of gradient H. Actually, our method can have the same moderator as Stangle et al.'s by choosing some special decompositions. But by choosing different decompositions, our method provides a different way to construct moderators. Here are experimental observations. We define a measure rule to record the proportion of edges that satisfy L sub E greater than L, and we color those edges to be pink. As shown in bottom right figure, their solver tries to make L sub E greater than L for all edges. When that is satisfied for most edges, the energy and the L sub maximum drop suddenly. We conjecture the reason is when L sub E is smaller than L, it uses the Hessian of G sub E, which is 0. Consequently, their solver uses many iterations to remove the influences of the lost Hessian, and such process leads to noisy results. Despite the noise, the result is also a discrete Chebyshev net. The different results are caused by the freedom of deforming chord mesh with only edge-length constraints. We present more examples here. Our method is faster and does not generate noise in practice when the L sub maximum is greater than 10 to the power of -6. We propose two speed-up strategies to accelerate the optimization. The first is adaptive P strategy. We've observed that the value of P significantly affects the convergence rate. A small p leads to a rapid decrease of the L sub maximum at the beginning, yet cannot penalize it to be very small. A large p produces an opposite behavior. We propose an adaptive p strategy, which uses a small p at the beginning and adopts a large p in the process. The second is adaptive variable reduction. We observe that the edge length deviation of most edges will be tiny after several iterations. It indicates that these edges do not need to be optimized in the subsequent iterations. So we optimize all vertices at first, and then we collect the vertices of specific edges and their n-rings into a set. Finally, we optimize the vertices in that set while fix others. Using this strategy reduces the optimization time and generates almost the same result. With these two acceleration strategies, our optimization procedure contains 3 stages. The first is optimizing all vertices using a small p. The second is updating all vertices using a large p. And the third is optimizing the selected vertices with a large p. Here we show a demo to demonstrate that our method can achieve interactive editing of discrete Chebyshev nets. Next, I will show our experiments. In the adaptive P strategy, the values of P affect the convergence rate. In general, the small p is set to be 2. Different large P values are tested. We observe that large P leads to faster convergence. However, a very large P usually causes numerical issues in practice. Hence, the large P is set to be 50 by default. We test 3 parameters in our workflow with more options. Since the results are similar for most parameters, we set them as shown. Our method contains 2 acceleration strategies. Here we perform an ablation study to show how each strategy improves the convergence rate. 4 methods are studied as in the form. It shows that both strategies contribute to optimization acceleration. We select 4 methods as competitors. The first one is an isometric editing technique. An ARAP energy of Sorkin and Mark can be directly used for chord meshes. The second one is Basile et al., which uses local global solver to constrain edge length. The third competitor optimizes the following energy, which is the most natural form for preserving edge length. In experiments, we choose P equals to 4 and 8. We use our solver to minimize it. The fourth competitor is solver of Stangl et al. We use both acceleration strategies for the solver. From the comparisons, they cannot minimize the maximum edge length deviation to be small enough. Our method succeeds in achieving a much smaller DL sub maximum using less time. Here we optimize E sub different with different P's, and we found that increasing P cannot contribute to improve the convergence rate. Now I will conclude our work. Our method provides a novel approach to edit discrete Chebyshev nets interactively. To make the maximum edge length deviation job to be very small, we use LP norm to define an objective function. Then the objective function is minimized by a second-order solver with a novel moderator. Consequently, our optimization method is able to reduce the maximum edge length deviation quite quickly. The feasibility and practicality of our editing tool are demonstrated by successfully deforming various discrete Chebyshev nets. There are some future works which are not solved. First, large deformation or hard positional constraints of handles may cause the algorithm to fail, and the cause may collapse as we circle. Since we cannot guarantee isometric deformation. Second, when moving a point handle, it appears that the shape is globally affected even if the vertices are far away from the handle. How to control this is an interesting future work. That's all. Thank you very much.
Thank you very much, Ruizeng, for stepping in. That worked perfectly well. Now we have time for questions. Maybe I start with the first one. You spoke about these constraints, user constraints that can be edited. What kind of constraints is that? Is this just the positional information of some vertices, or do you have also some other kinds of constraints that like based on lines on other features?
The positional constraints are specified by the users, such as the fixed points or moving points during the deformation. And the edge length constraints is just the, because we need to edit discrete Chebyshev nets, so we need to constrain the edge length of the nets.
Are there other questions?
Hello? Wait. That might be a bit outside of what you just talked about, but I'm not familiar with Chebyshev nets. What are some uses for them in rendering?
Actually, they are code meshes, and they cannot be extended along the edge directions. So they can be used to construct many buildings, or I saw many papers to show that they can be used in the packaging, and like I just showed in the video. That's because the edge lengths are not easy to change, so they can modify. So they can describe the inextensible properties, and that may be important for many kinds of material. Okay, that's all.
Thank you.
Hi, thanks for the presentation. Have you considered actually fabricating one of these examples with like some wire material, and like what would be the challenges for doing so?
Sorry, I didn't follow the question. Can you say that again?
Have you considered actually fabricating these examples that you showed?
Oh, we didn't test the. I think our method can just deform the discrete Chebyshev knights in one way, because deforming such knights using only edge length has much freedom. So I actually didn't test the real performance of such method, and I think maybe for different kinds of material, the Chebyshev knights may have different performances.
Thanks.
Questions from the audience? I'm also checking the Discord channel. No question? Also not in the chat. So yeah, thanks again for the presentation. Thanks all the presenters in this session, and have a good lunch break.